Now that we've talked about BGP peering a little bit, let's work through the BGP update messages and just BGP messages in general and talk about not only what they look like, but also how they're processed and things like that. So let's begin here. This is a BGP message. Now, many people tend to think of the BGP update as the only kind of message that is available out there, but that's not true. There are, at this point, at least 4. There have been proposals for more. This is the BGP message format. The message begins with this 16 or this marker, which is all ones. Now, this used to be used in EGP and older versions of BGP to carry information, but it was marked to a marker with all ones for backward compatibility. If an older version of an older BGP speaker, BGP v3, v2, etc., receives an update or a BGP message, I shouldn't say an update, but a message with something other than all ones in here, then it'll simply reject the message. So therefore that prevents BGP v3, v2, and etc. speakers from talking to BGP version 4. There is also this length in here. This is the length in octets. We will find this is true of every length field in BGP. That all the length fields are in octets. The length field in the older original BGP RFC was allowed to be set between 19 and 4096 octets. Now this field can support a lot more than 4096 octets, but it was believed that the maximum transmission unit for most types of processors or most types of media were not supporting anything more than 4096 octets, so there was no reason to have anything larger, so it was made to be an error if it was larger than 4096. Now RFC 8654, however, goes back and allows this entire field to be used for length in octets, making the new maximum 65,535 octets. There is a new capability, which we talked a little bit about capabilities. We'll talk a little bit more about capabilities here, that tells the BGP speaker what the maximum length will be in this BGP message field. Finally, there is this type. There are 4 types. There's 1, which is an open message, which we've already talked about. 2 is an update, which we'll talk about in just a moment. 3 is a notification. We've kind of talked about notifications on and off, so we will get there and talk about notifications a bit deeper in a later session. So 2 is the update. 3 is a notification. And 4 is a keep alive. Now there was a proposal to create a type 5, which would have been opaque. And this would have been used much like a community or an opaque type of thing in OSPF, an opaque LSA, so that BGP could just be used to carry random information. The original purpose behind the opaque was to carry security information, and this was specifically for SOBGP. However, this was rejected by the community, and there is no Type 5 today, and nobody's implemented it, and the draft is long gone. Now, if I look at the BGP Open, the BGP Open, like I said, is one of these types. So there's a BGP message, and within the BGP message, if it is BGP message type 1, it is a BGP Open. The BGP Open contains a version. This is currently set to v4. It is my autonomous system is next, and this is, of course, 2 octets in most standard versions of BGP. However, there are drafts or RFCs that allow this to be 4 octets. This is one of the things that's changed in the 4-octet AS number system. And, you know, the octets and the AS number are set there because it felt like for a while we were going to run out of the 2-octet space, which allows 65,535 or so BGP autonomous systems, minus some reserve stuff and this, that, and the other. So there's been a draft out and an RFC out to change to 4 octets, which allows you to have, I would think it's 4.2 billion or whatever it is. It's 2 to the 32nd. It's the same as the IP address space number of autonomous systems. So this is out there. Most implementations now support this. There is also a capability that tells the speaker what number of octets the autonomous system numbers will be carried as in the open and in other spaces. The hold time is the amount of time that the BGP session can be kept open without receiving a keep alive. This is in seconds. Then I have a BGP identifier. This is my router ID, and it's formatted as a IPv4 address. My optional parameters link tells me the number of octets in optional parameters. So the optional parameters are primarily capabilities, but there are a few other things here you can find online of different kinds of capabilities that are parameters that are out there. Now, the BGP reachability, the BGP Reach TLV, or the BGP update, as we often call it, although again, update is an overloaded word. BGP message carrying an update is called an update, and the BGP reach is also called, reachability information is also called an update, which is a TLV within the BGP message type. So you can get quite confusing about these overloaded words. So I'll just call it a BGP reach or reachability TLV in this series so that you'll understand the difference and try to keep it different. Now, this begins with a withdrawn route length and then withdrawn routes. So within a single BGP message or BGP update or BGP reachability TLV, I can carry up to 65,000 octets. Remember, this is not 65,535 withdraws. It's 65,535 octets. Or actually, it's not even, because that would be 16.2. Yeah, anyway, that of withdrawn routes. So each withdrawn route can be either 32 bits or 128 bits based on whether they're V4 or V6. So these are my withdrawn routes. These are called explicit withdraws. I talked in an earlier session on BGP about implicit withdraws a little bit when talking about multipath. So this is where your explicit withdrawals are carried, is here in these two fields in the reachability TLV. Then I have a total path attributes length, which is 2 octets, followed by my path attributes, and we'll talk a bit more about path attributes. These are very important, and you'll see a lot of different path attributes, and they play a big role in best paths, so we'll be spending a lot of time talking about path attributes. Then I'll have my network layer reachability information. Now this NLRI is either formatted, well, is typically formatted as V4 or V6, but we'll talk about MP in just a second, multi-protocol, which is what allows you to run V6. But these, any routes or any reachable destinations or NLRIs carried within this section of the packet share the same path attributes. This is really important because this relates to the way things are packed and the way things are processed in a BGP speaker, and we'll be talking about that a bit. Now, what are these attributes? Some of them are things like origin, which can be EGP, IGP, or unknown, etc. It can be the AS path, which we've talked about the AS path a little bit in making sure things are loop-free. Can be a set or a sequence. This is almost always a sequence at this point. There used to be a thing called an AS path set. It's pretty much been deprecated. I don't think anybody implements it or uses it any longer. They might be able to receive it, but I don't know anybody who generates an AS path set at this point. Another one is the next hop. We've spent a little bit of time talking about link local next hops. There are other ways in which the next hop field can be used or changed. The multiple exit discriminator, or the MED, the local pref. And we'll be talking about some of these, by the way, as we go through the BGP best path process as well. The atomic aggregate and the aggregator. Now, these two, again, are part of the set rather than sequence. So if the AS path is a set rather than a sequence, you would normally expect to have an atomic aggregate and an aggregator. Again, the aggregation in BGP using this system of using atomic aggregates and aggregator along with an AS set rather than a sequential AS path had been pretty much deprecated. So you won't see these a lot. Now, there is the MP-Reach TLV, or the MP-Reach, MP reachability, multi-protocol reachability TLV, which is a different message type within BGP. The main difference here is you're going to find an address family identifier, which is 2 octets, and a subsequent family identifier, which are going to tell you, and again, you'll see that here you have withdrawn routes length, total path attributes, and LRIs. Here you'll see that you have your AFI, your subsequent AFI, which then tells you, like, the address family identifier tells you what kind of reachability information you're carrying. And we'll go over some of these in just a second to give you a sense of what kind of information can be carried in a BGP MP-Reach TLV. The length of the next hop and the network next hop are now placed separately from my path attributes. Why? Because it could be that I'm using a different address family for my next hop. For instance, I could be using IPv4 next hops in an IPv6 NLRI, or the other way around. So this allows me to have different kinds of next hops onto each of those things. And I have this reserved 1 octet, and then I have my NLRIs again that allow me to have all of those attributes above carried with or in the same place. And so this gives me some sense of how I carry NLRI information. So I'll still have my withdrawn routes, my total path attributes, and then I'll have my AFI, my SAFI, my AFI, my SAFI, and then I'll have my length of next hops, my next hops, and a separate NLRI thing. So this is the MP-Reach. This is an alternative to the standard reachability. Now, this is a list of all the AFIs, and you'll note that IANA maintains this list again. IANA is a really good source to find things that you're looking for about routing protocols, because what they do is they just maintain all these registries of routing protocol information. So every routing protocol pretty much uses the IANA registries for their information like this. Now, you'll notice that I've only listed some of the AFs. Not all of the AFs are implemented in any implementation of BGP. 1 and 2 are widely implemented using MP-Reach. These are IPv4 and IPv6. Then you'll find one that is primarily used in BGP, which is 25. And this is defined in 4761 and 6074, and this is for L2VPN. Then you'll find your MPLS TP, which has 3 different address families: pseudowire endpoint identifier, LSP endpoint identifier, and TP section point identifier. And these are defined in 7212. And then you'll find multi-topology V4 and V6, which are defined in 7307. And then you'll find BGPLS, 48-bit MAC and 64-bit MAC. I believe you'll find things like EVPN use these AFIs, AFIs and SAFIs to carry Ethernet addresses or MAC addresses of various kinds. But one thing I want to point out here is that not all AFIs necessarily carry reachability information. This is kind of strange. You'll find this routing policy AFI, which was defined in draft IETF IDR APD -02. I don't know if this was ever implemented by anybody, but the idea is that you can actually carry policy that is strictly just kind of routing related within BGP. And again, there was a new message type that would have handled these, a message type 5, which was opaque, but that was rejected by the community. You won't find a lot of things that are not reachability related within the AFI, but there are some out there. So it's good to make sure you remember this in the back of your head, that that AFI can carry something other than strictly reachability information. The 4-octet AS number that I discussed just a second ago is defined in RFC 6793. You can go look that up. Essentially, you have AS number that instead of having a single digit would be like 1:10 or something like that. And this is the first 2 octets and the second 2 octets. So you'll see that out there in various places. AS0 has a very interesting history. Originally, if you put AS0 as your origin, it meant that this was a non-routed network. That meant you would never, ever send traffic to this destination. It was used to just carry like magic numbers and remote triggered black hole type things around in BGP. This was carried into 6491, which is routed origination attestations. We'll be talking about BGP security in a much, much later session of this BGP training. So you can just kind of keep that in the back of your head. But it turns out in 7606, it was redefined to say that any path with AS0 is considered malformed and you should just do a notification. Now there's one other thing that you need to know about, which is attribute scope. There are 2 pairs of ways of looking at attributes. They are well known or optional. Now, well-known means that every BGP speaker should be able to support that attribute. Whatever that attribute is, it should always be supported. For instance, AS path is typically a well-known, what's called a well-known attribute. Optional means that not every BGP speaker needs to be able to support it. Now then there's transitive, which means whether or not you support this particular attribute as a BGP speaker, you should go ahead and continue carrying this attribute within your updates or within your MP-Reach NLRIs or MP-Reach TLVs to your peers, even though you don't understand it. Or non-transitive, which means that you should block or you should not continue carrying it. So it's interesting because all well-known attributes must be transitive. I don't know of any well-known attributes that are not transitive, because if they're well-known, everybody should be able to support them. So therefore, you should go ahead and carry them over. Now, there are optionals that are non-transitive. Well, I say that, but there are some, like multiple exit discriminator, that actually is well-known and non-transitive. That means that it is well-known, everybody needs to know how to speak it, but you don't normally forward it outside of an eBGP session or outside of a single eBGP hop. So there are some actually that are well-known and non-transitive. So you need to pay attention to these and think about whether you're dealing with an attribute that is well-known or optional and transitive or non-transitive. Now, there are a couple of other things to deal with. The first is, how do I think about the BGP process handling updates inbound and outbound? So let's deal with the update process first, inbound and outbound. Now, a lot of people don't exactly understand how BGP processing happens within a BGP speaker. But what's interesting is you'll get to people and they'll talk about a BGP update that goes end to end in the network. There's no such thing as a BGP update. The BGP update itself is never sent from the originating speaker to the final speaker in the network. So let's look at how this processing works a little bit and try to understand exactly how a BGP speaker handles updates or reachability information or routes, as they're called, because a route is really an NLRI plus its attributes. So that's really the technical meaning of a route. So I'll just try to call them routes because that's kind of what they are. So if I look at the MP-Reach TLV, I have an attribute and a set of NLRIs. So what I can have is I can have attribute 1 tied to NLRI 1 and 2 in this update, and attribute 1 tied to NLRI 5 and 6 in this update. So NLRI 1 plus attribute 1 is a route. NLRI 2 plus attribute 1 is a route. NLRI 3 plus attribute 2 is a route. So I hope that makes sense. So when the BGP speaker receives this information, it is not simply going to stuff these updates away as they exist, this MP-Reach TLV, as it exists, as it's received off the wire. Instead, what's going to happen is it's going to take the attributes that are unique and it's going to place these attributes in an attribute table. So you'll have attribute 1 in your attribute table, and you'll have attribute 2 in your attribute table. The NLRIs, likewise, will be stuffed into about a routing table or into a BGP NLRI table, a route in or a route out or whatever it happens to be. There are 3 logical routing tables defined within the BGP specifications. Most implementations only have 1, and they use various ways of walking the table to fake out or to make it look like there are 3 tables within the BGP implementation. So what happens is this attribute table will point to each of the routes that hold that set of attributes. And likewise, these NLRIs will point to, it's a doubly linked list, will point to the attribute set that match that particular NLRI. So now let's look at the outbound processing and understand why that's important. Why that's important is when you walk the BGP table to build updates outbound, you don't actually walk this table right here with the NLRIs in it. Instead, you walk your attribute table. So what you do is you say, what are my routes for attribute 1? I'll say NLRI 1. Well, let's say, for instance, that instead of things coming into NLRI 1 and NLRI 2, I walk NLRI 5 next. So my outbound update to my outbound speaker, my my eBGP speaker or iBGP speaker that I'm sending routes to may be packing with attribute 1 with NLRI 5 and 1, and attribute 1 in the second update might be packed with NLRI 2 and NLRI 6. So these are not consistent. Even though these two do not match these two, they contain the same information overall. So this is very, very crucial to understand about the way BGP handles its updates. Now, this is partly in order to do packing. So if I receive NLRI 1 and NLRI 2 and then 5 and 6, and then I go back when I walk the attribute table, I want to build as few BGP messages outbound when I'm sending updates as I can get to. So what I'm going to do is pack as many NLRIs into a common attribute set as possible. The more attributes, the more communities, the more next stops, whatever you have, the less efficient packing is going to be. So that's very important to remember. Peer groups are also used this way. So what happens is I take all my peers that have the same attribute set or the same filter set, and I call them a peer group. And what I do is I allocate my packet once, my packet memory once, and I simply replicate that packet to every one of the peers outbound. So this is kind of a form of multicast replication, if you will, on BGP. And this makes things much more efficient. Now, another thing to think about is that when I build these messages from a BGP perspective, I'm going to build a message, and then that message is going to be sent through a socket to TCP on the local network stack. Well, TCP is going to send that stuff to a segment queue internally, and it's going to wait until the segment fills up or there's some timer that fires that will fill the window. Because what I don't want to do is send a bunch of short segments. I want to be using my TCP windowing to make my TCP connection and streaming to be as efficient as I possibly can. So I'm going to wait till the window closes, or I'm going to wait until my timer fires and says, okay, this stuff's been laying around long enough. Now, the problem with this for BGP is that slows down convergence. So many TCP implementations will have an API that allows a TCP client to do what's called push a segment. It'll say, close the segment now, send it. I don't care what your internal timers say. I don't care what your window says. Do it now. So most BGP implementations will take advantage of this API to push segments much faster than TCP normally would send them, particularly in 1s and 2s when I'm just sending an update with a couple of NLRIs in it. So this is one way in which BGP and TCP interact in order to make BGP converge more quickly. Well, that's it for BGP updates for the moment. We'll come back and talk about more BGP operational details in just a minute.